Okay, so let's look at question number 10. So this is similar to the other ideal gas law question I had, but this time they're just asking what is the gas law, or what gas law is PV equals nRT. So this gas law is called, this is derived from the kinetic molecular theory, which basically has different assumptions. So this theory is based on the assumption that your gas molecules are constantly moving. You want to also assume that the space in between gas molecules is greater than the molecules themselves. This is also assuming that kinetic energy is determined by temperature. And lastly, assuming that all collisions are elastic. So PV equals nRT. It comes from basically combining all of the different gas laws, such as Boyle's, Charles's, and Avogadro's. So I already went over what each of the different variables means, but I'll just say it briefly again. It's pressure times volume is equal to number of moles times the gas constant R times temperature. So let's see what our junior tutor said. Ideal gas law is a simplified equation that was derived using the assumptions of the kinetic molecular theory. 1. The space between gas molecules is much larger than the molecules themselves. 2. Gas molecules are in constant random motion. 3. The average kinetic energy is determined solely by the temperature. Note this statement implies that all molecules have the same kinetic energy at a given temperature, regardless of their mass. 4. All collisions between gas molecules and between the molecules and the walls of the container are perfectly elastic. No energy is lost because of the collision. Ideal gas law combines all the gas laws, Boyle's, Charles, and Avogadro's, and is expressed as PV equals nRT. Value of the gas constant R differs depending on the unit of measurement of other parameters. Table below lists all the possible values of R. So this is what I mentioned earlier, like depending on what a question like gives you, if they give you a value in joules or in meters cubed, like the R value will change depending on what the units are. So this 0.0821, this is the same thing that I calculated in the previous question, and it is in liters times ATM over mole times Kelvin. 8.3145 is another common R value that you may have to deal with, and its values are in joules over mole times Kelvin. And then the last two, they aren't commonly used, but basically it's 8.2057, and the units are meters cubed times ATM over mole K. And then the last one is 62.3637, and its units are in liters times torr over mole K, or liters times millimeters of mercury over mole K. So again, like, I have rarely used the last two R constants, but it's also helpful to know them and to just know when to use which gas constant. So this solution is correct. Okay, so I think we have time for one more question.